Welcome to my talk about the design of a solar air heater using feature mapping methods. A solar air heater is a flat, large device. It works with a greenhouse effect. And the basic concept is that it has an absorber. And in this case, the absorber is a carbon fiber mesh or mosquito net simply. The idea is the following. Sun shines through a glass pane and heats up the absorber. Then cold outside air is enforced to pass through the absorber. By this, it takes the heat, and this warm air is then blown into the building. A variant is that the air is circulating in the building. Solar air heaters are simple, cheap, sustainable devices. So simple, so cheap. It's actually even easy to build it by yourself. So it's a really cool do-it-yourself project. They support heating in autumn and spring, and they can provide ventilation by warm and fresh air. Usage is, as far as I understand, mostly in the industrial agricultural area, especially in India, but far less known for private houses. And what I want to do, and this is really the background of this work and where I'm here now and present this, I want to present the usage of solar air heaters as a sustainable measure. And what I really would like is to be able to provide open source blueprints so everybody can build and construct solar air heaters. The approach I can deliver here is to set up a numerical framework which allows us to design absorbers. For the state of the art, a little bit uncommon, the best source I really found is Build at Solar. It's a web page with a lot of professional do-it-yourself content, completely unstructured, unfortunately, but with really cool content. For example, what two guys there did, they built several kinds of typical solar air heater designs, double measured it twice with professional devices, and the devices they measured is one is a screen design. That means what I presented before, that the absorber is kind of a mesh. Alternatively, absorbers can be soffit material, so it's a metal sheet with holes in it. A third variant, also quite known, is to have black tube channels. And the most easy approach is that one has baffles which enforce the air to meander through the solar air heater. And by measuring and comparing these and further designs, it was found that the screen absorber is by far the one design with the best performance and also quite easy and cheap to construct. And the assumption which is postulated is that one needs to find the balance between the amount of absorber, for example, how many layers to have, and the pressure drop of the solar air heater. And finding the balance, well, this triggers me as an optimizer. I found almost no scientific publication which covers screen absorbers. Unfortunately, probably. The approach I do here, and this is my golden hammer, because I come from the feature mapping area, is I describe the absorber as a high-level geometric object. It consists of a start point with coordinates, an end point with coordinates, and the connecting line PQ allows us to define elevations by A, and with certain numbers of elevation, we can construct various kinds of absorber designs. This abstract high-level object is then by the feature mapping method projected on a pseudo-density mesh on a fixed finite element or simulation mesh, where outside the absorber we have void, inside we have a defined material, and we also cover the handle properly the stages in between partially overlapped elements. The material properties we have is interpolation, so bimaterial interpolation between air property and absorber property, where we have partial absorber property because the absorber itself is only a mesh. The mesh is thin and we have a certain number of layers we want to model. Feature mapping by itself allows fully differentiable configurations. That means we can do fully gradient-based optimization. The details for this special object, we call it a spaghetti object, can be found in a recent publication by us, but also in a review paper about feature mapping methods for structural optimization, which is probably the best starting point for feature mapping. We use then the absorber for the flow simulation, and the flow simulation we do by use of the Lattice Boltzmann method. And so the Lattice Boltzmann method is an iterative procedure where we have collision and distribution of virtual particles. And with some numerical efforts, then what we get is we have an element-wise directional velocity, which is the output. There exists a porosity model for the fluid simulation, which has been adapted to topology optimization by Georg Pingen, Kurt Maute, and Anton F. Grabov, and this is what I use here. I model the porosity of absorbers, so usually one considers 2 or 3 layers of absorbers, then via intermediate density. So we stay in the gray regime itself. The reference model here is a flat absorber. That means air is considered to come from below. We have an enforced inlet boundary condition. Here is the pseudo density gray absorber, our outlets. When we enforce the flow through the absorber, we have a high pressure before the absorber, a low pressure afterwards. The velocity is 0 or close to 0 at the boundary of our domain, and also very small when it's enforced to pass through the absorber. This model is not really realistic, so I doubled the height. Common would be 2 meters by maybe 20 centimeters. Here we have 2 meters by 40 centimeters, just to see more what is going on. And also the dimension of inlet and outlet cannot be extruded directly to 3D. When it's only circular in 3D, in 2D it would have to be smaller. Common for solar air heaters is that one has an outlet fan, but also inlet fans exist, and I actually find this a better idea because it's easier to apply several fans to scale the inlet velocity. Speaking about the fan, here is a study of the system with different absorber densities for a diagonal absorber and various inlet velocities enforced as an inhomogeneous Dirichlet boundary condition. And this is the reaction we get. A fan itself has also a characteristic, and the fan characteristic has a maximum static pressure when we have no airflow, and when we have no pressure drop in the system, we have a maximal airflow. And idealized, the connection between these 2 extreme points is a diagonal line. And with the diagonal line, I find the working point of our fan by cutting with the current density, with the current pressure drop. So, and this allows us to scale the velocity to reflect the density, to reflect the characteristics of the fan as a design-dependent, absorber-dependent function. With this rescaled velocity, we can solve then the convection diffusion equation, which is here a stationary convection diffusion equation. We solve for the temperature T. We have the material property, thermal conductivity, specific heat capacity, and material density. I have a inhomogeneous directly boundary condition for the temperature on the inflow, and we also have the right-hand side source at the absorber, the nodal right-hand side, which we scale actually effectively by the density of our absorber. The thicker the absorber, the more material we have, the more we can absorb heat. The less absorber we have, the less heat we can absorb. Here we see that we have on the inlet cold air, and when the air is enforced to pass through the absorber, it takes the heat from the absorber and transport it to the outflow. Here we have a little bit of a shadow where not that much flow is going through the absorber. This makes the absorber hotter. When we have just a linear heat source at the nodal line of our absorber, and we consider that the general media is air, which is an excellent isolator by itself, we have the following situation. The velocity is close to zero at the boundary, in shadow zones, and in the absorber, partially when the velocity is small. That means we have no heat transport. In the end, in the limits, that means we would have something like a static heat equation, but we have then a load in the void. The load is in watt, but this can result in very high temperatures. This is similar what we can observe in density-based elasticity topology optimization when we have a force displacement in the void. It's simply over-exaggerated. Here we see first a diagonal, or do not even see the diagonal absorber in the temperature field, because in the shadow, at the end of the absorbers, the temperature goes so high that we get here unrealistic 440 degrees, and also in a flat design, only a small amount of velocity is within the absorber, transporting more and more and more heat, which ends up to 310 degrees inside the absorber, which is realistically too much. As a remedy, I have implemented a nonlinear heat source as a fixed point iteration model to keep the temperature at the maximum limit of the absorber. So let's be here 100 degrees for small temperatures. The nodal heat source, every node on the center line of our absorber has a certain value depending on the density, which is here a little bit about 3 watts per node. For very high temperatures, it has no heat source anymore. And with an iterative scheme where we have a individual nodal damping parameters, each with their own history, similar to the moving asymptotes in the MMA method. This simple fixed point iteration scheme quickly iterates to the desired temperature. We see it here in the example of the flat absorber. The right-hand side, in the beginning, it's 3.2, but the hotter the absorber gets, the smaller the load gets, which results in a temperature of the center point of a certain point, I think it was here, to be fixed with 100 degrees. With this model, we can do now a parameter study. We have one simple absorber, and we vary the height of the front point and the height of the back point, and make a study of it with a density of 0.3 and 100 degrees, density of 0.4 and 100 degrees, and a density of 0.3 but 150 degrees. We see first that we have a dependency on the density, which is what was expected. We also see we have a dependency on the enforced material parameters, so we can by the magic numbers of the model control the design, where we need to be very careful about. We see that a straight diagonal is in this numerical experiment not optimal, but and also that the flat design is penalized because due to the nonlinearity, the total amount of heat is so small that the overall objective function is small. Objective function, yes, I forgot, is a heat flow, which is at the output. At the output, the integral of the temperature times the vertical velocity component. Here we have the diagonal design, which one can consider as kind of a reference design. And the better design in the parameter study is here a little bit higher. And the result is that the velocity is, as I said, the flow is not that much enforced to pass through the absorber, but it may pass the absorber. This allows the absorber to heat up more. We gain more temperature in the system. So the scaling here is always the same for both configurations with the same color scale. And we get a high percent higher heat flow with this configuration. When we enlarge the number of variables, I did a simple gradient-free optimization with one bending node inside. This configuration has the same, quite the same performance as a full diagonal from here to there. But I like the idea, the physical idea which is behind of this design. With more parameters, I have a gain of almost 70%, but I'm not yet sure how far to trust it, how far the numerics tweaks the result. For example, we have a small amount of heat pathing at the ghost layer around the obstacle. It does not look here that it influences much the result, but okay, it needs to be checked. One needs to be careful. I built a solar air heater by myself. That is a reason why I'm really big fan of it. So in the first page image, this was my solar air heater, and I measured it. And to obtain the airflow from a measurement, I used a cheap CO2 measurement device with a logging. And after leaving home, I fit the air exchange rate of my home with a simple Eulerian function and can directly obtain the air exchange rate. And from this can recompute the airflow of the fan by the difference of this configuration with fan and without fan. At a total, I got for 1 year a heating energy of 130 kilowatt hours, where heating means only what I heat above the temperature I already have. When I consider the total solar energy, so from outside temperature to inflow temperature, I get 230 kilowatt hours. This could roughly be the case when one has a circular air radiation. I did not get much from December, January, February. So I simply had not enough sun there. It works good in spring and autumn. Here, I unfortunately miss some data due to technical difficulties. Okay, now question myself. I use the feature mapping method, my golden hammer. I only have a very few number of variables, so the question is really, do we need the sensitivity analysis? I did not use it yet. Up to now, I used gradient-free optimization. And I'm not that sure yet if using the density-based aspect of feature mapping is a good idea or not, or if maybe shape-aligned meshes are even better there. I'm not sure yet. What I miss and I do not have is really good material properties. So I do not have exact values for the fan. I guessed it up. And the question is also if one should with this respect, consider also the flow resistance inside the building. So from what I measured with anemometers, this has really a huge impact. For the material properties, for example, for the absorber, I did not have data for linear material properties and really not for nonlinear properties. And I'm not really sure yet how to model the n layers or 2 or 3 or whatever layers of the absorber with pseudo density for fluid and heat accurately, and if it's worth considering anisotropy for this. I guess what is really essential to assist this numerics are experiments to check, do some numerical models I can match experimentally setups, and hopefully one can find parameterized model material fan properties based on experiments. And when clock says it's time to end the presentation, to repeat, since this is different from what I did before, because here I really have a vision and I have ambition to get, I do not only want to model and improve solar air heaters, but I want to promote solar air heaters as a sustainable heating aid. I think these devices are widely underestimated and could do really something good. I want to do this by providing free blueprints for construction for normal people, companies, craftsmen, and I need help for it. I'm an engineer by myself, but from a mass department, I cannot start these measurements by myself. So one needs experimental validation, determination of model parameters, maybe advanced numerical modeling and simulation. And I would be really glad if somebody would be interested to collaborate, work with it, or take over the subject. And yeah, if you're interested, please contact me and let's talk about it. Thank you very much.